Today, I'd like to welcome Leigh Pelzel. Leigh is a member of Mensa of Western Michigan. He has a law degree from the University of Washington, describes himself as a semi-retired lawyer. Leigh is going to give us a short introduction of the physics behind nuclear energy and an overview of nuclear fission and fusion. He will then give us an update on where we stand with regards to generating power via nuclear fusion, which has long been considered the holy grail of power generation because it has the potential to be clean, safe, and limitless. If you have questions, please send them to me in the chat and I will ask them whenever Leigh has an opportunity for that. And so now I'd like to welcome Leigh Pelzel.
Thank you for that introduction. I appreciate it. So I think everything that I tell you today is, I think, going to be an accurate picture of reality, but I also will tell you that physicists will quibble with everything I say, I'm sure. Some physicists, not all. Some physicists will think I'm right on the money. Others will probably say that I didn't quite get it right, but that's okay. The idea is just to give you a general idea of what's going on. Also, I didn't know where to pitch this talk. It's going to be kind of introductory in nature. So it's sort of for the person who's curious, can understand math, but has never spent a lot of time thinking about physics or studying math, or, you know, not sort of a math geek like I am. That's where this talk is pitched. And if it's, you know, too basic for you, that's fine. That's fine. I'm sure we got other things you can do on Sunday. But I think for the rest of you, I think it's going to be interesting and a little bit entertaining even at points, because it really is fascinating stuff. Okay, so let's just kick this off. Our story sort of starts with Albert Einstein, of course, the incomparable genius who came up with all kinds of amazing things. One thing he came up with was E = mc squared. You've all heard that. I'm not going to assume that you all know what it means. It means energy equals mass times the velocity of light squared. So all mass has energy. In fact, it has quite a bit, as we'll see in a minute. Einstein first formulated it as m equals E/c squared, just to emphasize the fact that that's what matter is, energy. I didn't know that until fairly recently. So when you turn your phone on, your phone is getting lighter. It's losing mass because it's losing energy. And then when you plug it in, it gains energy and therefore it gains mass. So your phone is getting lighter and heavier all the time. Obviously, it's imperceptible, but it's real because matter is energy. So let's talk about what energy is. Energy is the ability to do work. And you can almost think of work, and this is where physicists will probably get mad at me, but you can almost think of work as physical work. So if you're pushing a wheelbarrow up a hill, that's work. It takes energy and it takes work. Kind of like you think of it in, you know, normal life. I have to expend a lot of energy to do a lot of movement. Work does have very specific meaning in physics, so, and I'll give that to you in a second.
You probably should know things about the World War II time, the Manhattan Project under the bleachers at the University of Chicago, where Enrico Fermi and a group of others created the first sustainable nuclear reaction, fission reaction, and things got the ball rolling there. Moved off to Los Alamos, secret project headed up by Robert Oppenheimer to create a nuclear weapon, which I'm sure you all know was dropped in two places in Japan, two different kinds of nuclear fission, one with plutonium, one with uranium-235. And there's a lot of history of nuclear developments over the years. In the 50s, the Department of Energy, I think that had a different name at the time, had a Atoms for Peace project where they wanted to use the nuclear bombs to dig a new canal across Panama or possibly Nicaragua. And they actually got to the point where this was almost going to be tried as a sample. I don't think it was in Panama where they were going to try it, but it eventually got canceled because somebody somewhere figured out that this would cause a huge amount of radioactive dust. Atomic Energy Commission at the time, I believe it was somebody mentioning. Let's see. I don't know where Lee has disappeared to. I actually did. Believe I talked with Edward Teller, who is described as the father of the hydrogen bomb. And he came to speak at an Asilomar many years ago. He's quoted as saying, "We don't know that radioactivity is bad for people." And I thought that was a fairly interesting comment.
So here's what I wanted to get at. Suppose you have 190 pounds of rocks, and we're going to just do some simple math, applying E equals mc squared. And our 190 pounds of rocks is equal to 86.4 kilograms. Here's the simple math. We're multiplying the kilograms times mc squared, and we end up with this many kilowatt hours. That's how much energy is in a bag of rocks that you buy. Well, a 190-pound bag of rocks that you buy at Home Depot. It's equal to this many calories, 1,851,277 billion, etc. Now we can compare that to 300,000 usable calories that in 190 pounds of Twinkies. That if we were to eat it, that's how many calories we would get, because of course the difference is we're talking about chemical energy versus nuclear energy. So there's a huge, the disparity is mind-numbing. Another fun fact, fission of one uranium atom is trillion times the energy of one TNT molecule. Okay, so, and then let's just go down here. I do some more math. Basically, that 190 pounds of rocks would be enough to supply the grid, the entire grid in the United States, with power for 7 months. 325 pounds of Twinkies or rocks, it doesn't matter, would power the United States for a year. And then I pose the question, does that mean 325 pounds of Twinkie of uranium could supply 1 year's worth of energy? Well, the fission reactions are not very efficient. 0.09% is converted to energy. The fusion's a little bit more efficient than that. Okay, let's talk about nuclear reactors for a minute. Almost all uranium is U-238, but there's an isotope called U-235, which is fissile, which means you can split it. So you put it in your reactor core, and a U-235 will split. It'll send out neutrons, and those neutrons will hopefully bump into other U-235 atoms and split them, which will split more, et cetera. That's called a chain reaction. They will also hit another U-238. Remember, that's the dominant form of uranium. And it will sometimes cause that U-238 to turn into plutonium-239, which also will split. So according to sources I've read, you get about 1/3 of your energy from the plutonium that's created out of the uranium, and you get about 2/3 out of your uranium. So here's something that I think a lot of people maybe aren't too familiar with, though. We all know what happens with that energy. It creates heat, right? And that heat boils water, and it creates steam, and we run a turbine. That is a turbine. That is where the steam comes, and it blows out both ends, and it spins this turbine. Okay, how does that generate electricity? There's a lot of excitement about molten salt reactors, and they're building one in China. And the idea is one advantage is you can use thorium in it, and thorium doesn't generate as many nasty waste products as uranium. They're also more efficient. You can run them hotter. But there's also a lot of interest in what are called walk-away reactors. The idea being that they're completely idiot-proof, and they can't fail. They can't cause a big blow-up like Chernobyl just based on sheer physics. And that's the idea behind them. So that's what this is. Okay, this is a simple schematic of a molten salt reactor. As you can imagine, molten salt is pretty hot. Although it's not sodium chloride, it's a different salt, but it's still very hot, of course. Here are control rods. Control rods are made usually of cadmium. You lower them. Can people see my cursor?
Yeah.
Okay, you lower them into the reactor core. They absorb those neutrons I was talking about earlier that are causing the chain reaction, slows the reaction down, take them out, speeds it up. Okay. What if they're stuck in the up position? And what if everything goes wrong? Okay. I don't know exactly what happened at Chernobyl, but obviously something went wrong. And it got so hot that it blew. It was not a nuclear reaction. It was
Chernobyl was a fire.
Was it a fire?
It was a fire.
But then but their cooling mechanism didn't work, and then the water heated to the point where the boiler just blew, spewing radioactive material all over the place.
It was not particularly a nuclear meltdown. It was much more of a fire caused by mismanagement and bad design, and that destroyed the cooling system.
Right, but my point is, it blew. Right, the pressure, the water pressure inside the cooling vessel got to the point where the metal couldn't take it, and it blew. Right, so here's this liquid salt floating around in here. It goes through a couple of heat exchangers, and then steam goes to your turbine. There's your electricity. Now, what I want to point out is something called a freeze plug. Okay, and it's a salt plug. And if this whole thing gets out of control, the rods won't drop, whatever, people are asleep, then this thing melts, and all the contents drain into here. And the salt contains the fuel itself. It's dissolved in the salt, so it just drains in here. So even if there's nobody mining the operation ever, it can't overheat and blow. There's a lot of interest in these sorts of things. There are new generations of nuclear reactors on the book, fission reactors on the books, and people are really excited about them. We face tremendous headwind in this country toward implementing anything like that, political headwind. I just want to touch on this, natural man-made sources of radiation. There are a lot of charts out like this. Most of them say the same thing. We get the vast amount from most of our exposure to radon. That's a form of uranium. Of course, I'm kind of cheating. That's a crystal. It has other things in it, but you can buy those on the internet too. They're quite beautiful, but you might want to get a lead box to hold it in. Okay, so here's what's happening inside the sun, right? You have a bunch of helium nuclei bouncing around. They're nuclei. They've been stripped of the electrons that normally surround them because of the temperature. The temperature in the sun is extremely high. It's about 27 million degrees Fahrenheit, and I'm talking about the core of the sun. When you get out toward the outside of the sun, it's not nearly as hot. And these guys are flying around, and boom, and they make helium plus energy. So why does it work in the core of the sun? Well, because there's incredible pressure there. It's the pounds per square inch. The core of the sun is literally in the trillions of psi. Your car tires are like 32. We're talking about a trillion plus. So the core of the sun, and tremendous heat. And so what that means is that the hydrogen nuclei are all jammed together. They're very hot and they're pressed. They're like sardines in there. And that's very important because it allows the protons to fuse. Now, you think about it for a minute. Protons are at the nucleus of an atom. We all know that like charges repel and opposite charges attract, right? Negative, positive, they come together, negative, negative, repel, positive, positive, repel. So how the hell are atoms holding together? Because they have all the protons at the nucleus, all atoms, and they have all the electrons spinning around outside. Well, there's a force that's stronger than that electromagnetic force, which is repulsing them. That's called the strong nuclear force. It's extremely strong, but it only operates at micro distances, about 10 to the negative 15th meters or something like that. So it's a very powerful force, but its reach is absolutely minuscule. Okay, that's why it's challenging to create a fusion reaction, because you have to overcome that natural repulsion that protons are going to feel. Remember, we just saw in my last image, we saw 4 protons come together. Well, 4 protons hate the idea of coming together. They're repulsing each other, right? But so you have to smash them. You have to get them really close, and you have to smash them hard to make it happen. We have been doing that in fusion reactors for a long time now. We can make it happen. It works. But the problem is you have to recreate the conditions inside of the core of the sun. Not exactly, but you get the idea. That's not easy to do, but more to the point, it requires an enormous amount of energy. So the nuclear reactors that we have, the hydrogen nuclear reactors that we have to date, consume more energy than they spit out. That's one of the big problems with them. You have to put in more energy than you get out, because it takes so much energy to heat the nuclear fuel that you're using. And they don't just use hydrogen, they use deuterium and tritium. Now, you folks, you remember what isotopes are, right? Deuterium is hydrogen with a neutron. Usually hydrogen doesn't come with a neutron. Tritium is hydrogen with 2 neutrons. And so that's what they're using. It's easier to get it to react, and you get more energy out of it. So let's take a look at that again. Here's the reaction. Can people see that?
Yeah.
Okay, so you got deuterium, tritium, they come together, and they release a helium plus a neutron. That neutron is actually problematic. It's trying to find a way to blow that up, but that's okay. So let's talk about the newest badass reactor that they have coming down the pike. It's the ITER, I don't even know how they pronounce it, ITER, International Thermonuclear Experimental Reactor, or tokamak. This thing, the start date was originally in '88, and as I write here, it's supposed to be completed by '35, but since it's obviously going to go over a little bit, it'll end up being about half a century before this project is completed. That's a long time. It's complicated and difficult. The cost is, of course, just gone through the roof. That's true with all public projects, of course. So let's take a look at this thing. You've got this giant reactor. The core is this vessel. It's a donut. And they use a vacuum to get everything out of there. Then they put their fuel in. Then they start heating it up. And they heat it up 3 ways. One, they have thousands and thousands of pounds worth of magnets surrounding this thing. And they're electromagnets. They're very powerful. They're magnets. When you move a magnetic field, you generate an electric current. That's what I was going to talk about earlier with power generation. In power generation, you use the mechanical energy to move magnets that generates electric current, right? But you can also move magnets to generate that electric current. independently of that. So you've got these moving magnets, generates an electric field. We all know, I think, that when you run electricity through something, you generate heat. Even in copper wires in your house, you generate heat, even though the copper is specifically chosen as a material because it has a very low resistance. You still create heat. You create too much heat, you start a fire. That's why you have circuit breakers. Okay, so these magnets are moving around. They're generating a lot of electricity, and that's heating up this plasma. But it's not enough. So they also use what I call a particle cannon, which fires deuterium ions into the mix. These are like high-speed linear accelerator type devices. They use a lot of energy, but they fire these particles into the plasma mix. That's still not enough. So they microwave it. And they use microwaves to heat it up. And they add pile all three sources of heat into this thing. And they're able to get it up to 270 million degrees. That's 10 times the heat at the core of the sun, which is mind-boggling. I'll never understand how they can do that. Now, well, I guess I understand. I just described it, but it's just amazing to me that they can get it up that high. Now, of course, if anything touches, if the plasma touches anything, of course, it's instantly destroyed. So how do you keep that from happening? Well, the plasma is very charged at this point, and you can keep charged particles in place using magnets. So there the magnets come in again. They're used to keep the plasma inside that donut, away from the walls, just on their own. And since it's a vacuum in there, I think you would have very little convection heating in the walls. So what the walls are just getting is intense radiation, in the form of neutrons slamming into the magnets and the vessel wall and all that. And part of the idea behind this experimental reactor is to see how well their hardware holds up, because 270 million degrees, there are lots of gamma rays coming out of there. The neutrons, we'll see. I obviously think it's going to work, but they have questions about how the hardware is going to hold up. Okay, so you are. Let's go back to this thing. So there's an artist's conception of this 270 million degree plasma spinning around. And the way the magnets work is kind of subtle, but one thing that happens is you've got a magnetic field here on the sides, and when a charged particle attempts to penetrate a magnetic field, it gets a perpendicular force. That's just one of the rules of magnetism. So particle tries to leave, but it gets pushed. And so you get this spinning, right? It's held in place by magnets. That's the very basic idea. Here is an image. Let's do that split. I think this is an enhanced image from a reactor in Britain, right? There's the plasma. You don't want to touch it. Those are protesters. Let's just leave it at that for now. Now, there've got to be some questions. Does anybody have a question so far?
There have been a couple of questions. One of them was about nuclear fission. Have there been any meltdowns naturally occurring on the Earth?
There have been naturally occurring reactors where uranium got concentrated and deposited on the seabed or something like that, where it's just been cranking out heat, kind of like a nuclear reactor does for an indefinite period. That's happened. Did I understand the question correctly?
I think you did.
Okay.
Another question, you were talking about the liquid salt reactor and how it's secure because of the freeze plug. How reliable is that freeze plug?
I have no idea. That's an experimental design. They are, like I said, they're building one in China. And it's a salt reactor. And I don't even know if they're using the freeze plug concept. I'm just throwing that out there. I'm trying to show that scientists are aware, obviously, of the hazards of nuclear energy, and they're just coming up with a bunch of different ideas to try to make it so that even if all the humans were asleep at the wheel, just based on the laws of physics, it can't go wrong. But as far as that freeze plug goes, I assume it'd be pretty reliable, right? Because they know where it's going to melt or what temperature it's going to melt at, and they know what temperature it has to melt at. So I would assume it would be pretty reliable.
Yeah. One of the questions is, what is plasma? It's clearly not what's used in surgery.
Right. That's a good question. Plasma, we all learned there were three states of matter, right? Grade school, we learned there was solid, liquid, and gas. I would call plasma a gas, but scientists seem to want to call it a fourth state of matter, not gas, not solid, not liquid. But what it really is a gas where it's so hot, has so much energy, the electrons have all been stripped off of their nuclei. So what it is proton masses flying around through the air and electrons all separated. That's what plasma is.
How is it, if the plasma is so incredibly hot, how is the output harnessed? How is the power taken out of the reactor to generate electricity?
Well, in this experimental reactor that's going to cost $40 billion or whatever, that's taking half a century to build, it's not. It's going to be released into the air. It's just experimental. This stuff's taking a long time to bring to market. But there's a tremendous amount of heat generated, and that heat will be used to boil water. Now, I'm not sure. Maybe you could maybe somebody could unmute and tell me exactly what the question is. I'm not sure if I understand
I think you really did, but let me see if I can.
You can unmute everybody as far as I'm concerned. I don't think anybody's going to.
Oh, it gets a little chaotic at times. Go ahead, Jeff.
Okay, what I was trying to get at is that very, very hot plasma is a big temperature differential that, offers a lot of capacity for doing work because of the temperature drop. How do we harness that when it's millions of degrees and is likely to vaporize anything it comes in contact with?
Yeah, honestly, I haven't thought about that, and I haven't read about that. I assume you could have. I know that the walls, the reactor register walls are getting hot as hell during all of this. Just, it's what the plasma is contained in just by the radiation. So there's a lot of heat transferred there just to the vessel walls. Maybe that heat could be used to heat water. Maybe the plasma could be extracted via magnets and slowly released into an expansion chamber where it expands up to the point where it's not going to melt everything. Right? You could control it. You could take out plasma using magnets, small amount of plasma, and then just put it into some, 10 by 10 by 10 foot cube or something, and let it expand into there. And it will, you'd have to make the vessel big, the expansion vessel big enough so that it wouldn't get melted, and then just extract the heat from that. Those are the only two ideas I can come up with.
One of the other ways is magnetohydrodynamics, where the motion of the plasma generates an electrical field, which will drive can directly generate electricity. Moving magnetics past an electrical coil will generate electricity.
Yes.
So that's another way to drain energy from the plasma.
That's true. I think Pete had a question.
Pete asked, where's tokamak being built?
Tokamak is being built in France.
Yeah,
Pete is waving. I'm not sure what Pete wants. I think he wants to say something. You can't hear me or something?
Just 1 second. Let me see if I can unmute him. Another question is, thorium is being investigated as an alternative to uranium as a fission fuel. Are there any fusion fuels that are alternate than the hydrogen isotopes?
That's a great question. Not that I've seen. Everybody seems to be bewitched by deuterium, tritium fuel because it does release more energy than your typical hydrogens. And I assume it's easier to get the reaction to proceed because you only need 2 particles smashing into each other instead of 4. And it releases more energy. So everything I looked at, they just talked about those 2 particular fuels. And tritium is very hard to come by. And so one thing that this reactor has are, they call them blankets, lithium blankets down in the reactor vessel. And the lithium gets bombarded by the high energy neutrons. And some of it gets converted into tritium plus helium, I believe is the reaction. So you cause a nuclear reaction in the lithium to generate more tritium because tritium is hard to come by. Yes.
There was another question about plasmas. If there was an accident and it was breached, wouldn't that create lots of fires? Would that be very dangerous?
I suppose it could. Everything in this place is metal. It would cause things to melt. But yeah, I suppose if the magnets failed and the plasma was no longer kept away from the walls of the reaction vessel, it would hit the reaction vessel and maybe melt right through. The one thing you have to keep in mind, though, is that at any given time, even in that big giant donut you saw there in that scheme, you only have a couple grams of fuel. So yes, it's insanely hot, and whatever it touches is going to be vaporized, but there's not much of it. It's not like this giant cloud of gas is going to expand and engulf the whole place and kill everyone.
Lindy asked, did we ever get to the difference between fusion and fission in generating electricity, how that works?
Well, yeah, I did have to skip over that partly because people seem not interested. They didn't want me to talk about fission. With fission, you split a uranium or plutonium atom, right? And that generates energy and nuclear waste, quite a bit of nuclear waste. But you're splitting the atom, and the atom literally splits, like a uranium atom, which is a big heavy atom, will split into barium, it'll split and form 2 other elements, barium, krypton, some of the noble gases. It's actually kind of random what it makes, but it makes 2 separate elements. From one element goes to 2 elements, and the process releases a little bit of its mass in terms of energy and creates a lot of nuclear waste. But basically, you're creating heat through a nuclear reaction, and then you're doing the same thing in fusion, but instead of splitting atoms, you're smashing them together to make new ones. Nothing's getting split. It's kind of the opposite. They're getting fused. That also, in the case of hydrogen or deuterium and tritium, releases a small amount of the mass in the form of energy, and that heat is captured to boil water. So at one level, they're the same. You're using nuclear processes to generate heat, which you can use to run a turbine. But on another level, they're quite different because the nuclear processes are quite different. And they also have practical differences in that one produces a lot of problematic and troublesome nuclear waste, and the other does produce a little bit of radioactivity, but we're talking about maybe 100-year hold period for some of the hardware and other things that get completely irradiated that maybe have to be buried for 100 years. It's completely different in that respect.
we had a question which may be a little bit off the wall. You may remember the Fleischmann and Pons cold fusion experiments from a number of years ago. Somebody asks about a company in Australia, Star Scientific, which says that they have a catalyst to to create a heat source interaction between hydrogen and oxygen and heat up. Does this have anything to do with nuclear fusion?
Don't think so. I've never, fusion involving hydrogen and oxygen?
Yeah.
Don't think so. No, that would be very hard to pull off.
Yeah. Another person, John, said that he heard that the moon has a tremendous amount of tritium, probably from being continually bombarded by cosmic rays.
The moon?
The moon.
It may well have a lot of tritium and cosmic rays. If we were to look back at that pie chart that you saw on where we get our nuclear our radiation damage from, cosmic rays were about, I don't know, close to 10%. Something like that. I'd have to look at my chart again, but it's significant. Cosmic rays are, you know, when I first learned about them a long time ago, I just assumed they were gamma rays, which is light. It's a form of light, but they're not. They're heavy particles that come from supernovae or God knows where. They come out of the cosmos and they slam into us. And one reason why you have less radiation exposure if you live at sea level like I do versus Denver is because the atmosphere helps protect us from those. But if you higher you go up, the less atmosphere you have protecting you, the more you get smacked by these things, these atomic fragments. So yeah, anyway, that's interesting. I bet there is a lot of tritium on the moon. The only thing is though, tritium has a short half-life. It's got a short half-life. So I don't think we could go up there and find some giant mother load of tritium because it's got a short half-life. And also it wouldn't be created all in one spot. Like you wouldn't find like a big vein of gold or silver. You wouldn't find that. If it's from the bombardment from cosmic particles, you would find it spread evenly all over the surface of the moon and decaying pretty rapidly. But it's interesting. I hadn't thought about that. Any other questions?
Another question was, you mentioned fusion. Is a fusion reactor the only way to get plutonium, or does it occur naturally? And I think maybe that meant to be fission reactor,
Yeah,
not fusion reactor.
I think that's meant to be fission. And they list it as an artificial element. I think you would find tiny amounts. I think you would find tiny amounts of plutonium naturally, but I think they'd be very tiny amounts. Like I said, if a U-235 atom splits, the neutron can hit a 238, causing U-239, which is radioactive. So at least we know that plutonium-239 must exist, at least a little bit in nature. But if we need plutonium, we do, practically speaking, we do have to use a fission reactor to generate plutonium. Yes.
Okay. We're running out of time, about the end of our hour. If we have any more questions, please.
Poor Pete keeps trying to raise his hand, but he doesn't get called.
Oh, I don't.
Yeah, I'm sorry. Anyway, you can email him, Pete.
Yeah.
You can email the moderator.
I thought I.
Maybe you asked this question. I don't know.
Pete Cowper, is that who's raising? I don't see anybody raising their hand.
Antoniak.
Oh.
Oh, there is a Pete. Yeah, there's a Pete Cowper up above, but then there's a Pete Antoniak. Antoniak. I'm messing up the name.
Go ahead, Pete.
Okay. One thing, I was a program manager for the inertial confinement fusion in Livermore, labs. And several things, perhaps misunderstanding. They were talking about the extreme heat inside the plasma. You don't want that heat outside the plasma. It may radiate through the vacuum, but that's not what you want. What you're doing is you're generating a lot of neutrons, and you have a lithium blanket that absorbs the neutrons. The lithium blanket heats up, and you then use that as your source of energy for driving a turbine. I'm not too sure. Maybe there's some confusion with the question. The other thing is tritium. Although it's expensive, you can buy an exit sign that has tritium in it.
That's true.
And so, you know, the need for creating tritium with the lithium blanket is not that big an issue. And also, I'm really concerned about, I'd like more information. I guess we're over now, but, you know, there are things like a traveling wave reactor that's been proposed. The process right now with your fission is that you're using boiling water, and that the Carnot cycle in boiling water, because you can't heat it up that high, is terribly inefficient. And so if you can get a much better higher heat, I'm certain the molten salt reactor would do that. But I'm curious as to, and I'll stop right now, when does that go online?
You mean the
Chinese
reactor that I'm talking about?
reactor, the Chinese molten salt reactor.
Oh, good question. Don't know.
Okay.
Don't know. But but I'll be interested to see what the results are. Regarding the tritium, I mean, this is something that's puzzled me, frankly, and I tried to resolve this before the talk, because you're right. You can buy tritium exit signs, you can buy little trinkets that have tritium in it. But at the same time, what I read from reliable online sources is that there's only about 22 kilograms of available tritium in the world.
Well, it's a gas, so it doesn't weigh a lot.
But I'm still having trouble reconciling that. If there's 22 kilograms only in the entire world, how is it that we're able to go on Amazon, you see tritium trinkets galore.
Yeah.
So
it's made in excess. They can't. In other words, it is made in excess. It's a product of some reactions, and it's made in excess of what they can use. I guess that's just the private enterprise find out what the price is. It's expensive, but you know you don't need a lot of it. It's a gas.
Yeah, I know you don't need a lot of it. But I do know in my readings that this lithium blanket producing the tritium is considered pretty critical, because they use that. They're going to use that as a fuel source.
You don't need a lot of tritium to make that, you know, again, MC squared. Anyway, I don't want to, you know, confuse things, so I'll back
Sure.
off. I don't want to, you know, take over the thing. So thank you.
Thank you for chiming in on that, though. I appreciate that.
Okay. Ilsa had a question. Go ahead, Ilsa.
I was a member of the plasma physics group in the early 80s with Walter O. Lewis. When I moved west, I lost contact. Do you know if that group still exists? And, you know, I guess that was when tokamak was a sculpture, traveling to science museums.
Yeah.
Do you know what happened to the tokamak at Princeton?
I'm sorry, ma'am. I am not a professional scientist, and I don't know those people. I'm just kind of a layperson tossing a layperson's lecture. So I'm sorry, your question goes beyond my pay grade. I'm sorry.
Oh, please, you're fabulous.
Well, that's what my wife says, but no one else agrees.
Oh, absolutely. You know, Walter O. Lewis spoke at the United Nations in 1974 to get people to understand the difference between smashing things and exploding them and crushing them and putting them together, you know, like the difference between concave and convex, and how fusion is actually part of the secret of the next form of energy that we're going to use, which is, you know, different groups talk about it in different ways. But I'd love to talk with you more.
Sure.
So you know how to get in touch with me. I'm in Sacramento, California.
No, I'd love to talk to anybody. Thank you.
Yeah,
maybe it's worth pointing out here, folks, that you know, part of the interest in nuclear power is because we've got, you know, the whole global warming thing going on, and as you all know, nuclear power doesn't produce carbon. So one issue is how fast are we going to get this online? We could build more conventional nuclear power plants, but politically that's not viable probably in the United States or a lot of other places. So it's almost a moot point. As far as nuclear fusion goes, it's going to come pretty late in the game, right? It's you know, even if we go with all solar and all wind then we're still going to need some sort of backup system because winds stop blowing sometimes and there's nighttime, so you need backup systems. Maybe you could just take excess solar and excess wind and put it in a giant battery. Or maybe we're going to need backup systems, which fusion could do. There are all sorts of dimensions to this, technical and political and strategic, and this stuff's complicated. I've just scratched a tiny bit off the surface.
We've had a couple tours out at Livermore Labs with past regional gatherings. And I think the last one was maybe about 10 years ago. And they've been working on nuclear fusion for 25 or 30 years. And I'm probably pretty loose on the number there. Near as I can tell, nuclear fusion on a commercial scale is 20 to 25 years away from any date that you ask. So in 10 years,
Yes.
in 10 years, it will be 25 years from then.
Well, that's the running joke, is that nuclear fusion is the power of the future and has been so since like 1950. And it's always been about 20 years away. There's a running joke on it. Yeah, I mean, some people are saying the second half of this century, maybe we'll see commercial nuclear fusion. It's totally cool. And I think that we'll make it. I think we'll be able to do it. But yeah, I don't think I'll be alive to see it.
I think that's perhaps a good place to stop. I want to thank our speaker
Certainly.
for this.
Thank you, folks. I appreciate you tuning in.
We appreciate your being here.
Thank you.
You.
Bye-bye.